Here is today's problem. We have a times a minus 1 times a plus 1 equals 120. We need to find the value of a that makes this statement true. We will start by expanding the expression on the left side. Let us focus on the two binomial terms first for simplicity. These terms are a minus 1 and a plus 1 in the product. We can multiply these two terms together using distribution. First, we multiply the a from the first bracket by the second a. This multiplication gives us the term a squared in our equation. Next, we multiply the a by the positive 1 to get positive a. Then we multiply the negative 1 by the a to get negative a. Finally, we multiply negative 1 by positive 1 to get negative 1. We can combine all of these terms to simplify the expression. The positive a and the negative a cancel each other out perfectly. This leaves us with just a squared minus 1 for the binomials. Now we substitute this back into our original equation format. Our equation is now a times the quantity a squared minus 1. This entire product is still equal to 120. We need to distribute the a into the terms inside the brackets. We multiply the a by the a squared term to start the process. Using exponent rules, this gives us the term a to the third power. Next, we multiply the a by the negative 1 term in the bracket. This simple multiplication gives us a negative a for our expression. Our new equation reads as a cubed minus equals 120. We want to set this equation to 0 to solve for the variable a. To do this, we must move the 120 to the left side. We subtract 120 from both sides of the equation. The right side becomes 120 minus 120. This simplifies nicely to just 0 on the right side of the equals sign. The left side becomes a cubed minus a minus 120. We now have a standard cubic equation set to 0 to solve. We need to find the roots of this cubic polynomial equation. We can use the Rational Root Theorem to test possible values. This theorem says we look at the factors of the constant term. Our constant term is the negative 120 at the end. We will test positive integer factors of 120. Let us start by testing the simplest value, which is positive 1. We plug a equals 1 into the expression a cubed minus a. 1 cubed is simply 1, and subtracting 1 gives us exactly 0. 0 minus 120 gives negative 120. Since this is not 0, the value 1 is not a root here. Next, we will test the value equals 2 in our polynomial. 2 cubed gives us 8 for the first part of the expression. We subtract 2 from 8, which gives us exactly 6 as a result. 6 minus 120 is negative 114. This is also not 0, so the value 2 is not a valid root. We must continue testing other factors to find a correct root. Let us move on and test the value a equals 3 in the equation. We substitute 3 into the expression a cubed minus a. 3 raised to the third power is equal to exactly 27. We subtract 3 from 27, which gives 24. 24 minus 120 gives negative 96. This result is not 0, so 3 is not a root of our equation. We will now test the value equals for it in the cubic expression. We plug 4 into the a cubed term to get 64 as our first piece. We subtract 4 from 64, giving exactly 60 as a result. 60 minus 120 equals exactly negative 60. Since negative 60 is not 0, 4 is also not a root. We are getting closer, but we need to check the next factor. The next integer factor to test is the number positive 5. We substitute equals 5 into our cubic polynomial equation. We calculate 5 to the third power to start the evaluation process. 5 times 5 is 25, and times 5 again is 125. So the first term in our expression evaluates to 125. Next, we subtract the value of a, which is exactly 5 in this case. 125 minus 5 equals exactly 120. Finally, we subtract the constant term 120. 120 minus 120 equals exactly 0. This means our expression evaluates to 0 when it equals 5. We have successfully found a valid root for our cubic equation. Therefore, the binomial a minus 5 is a factor of the polynomial. We must divide our cubic polynomial by this new known factor. The polynomial is a cubed minus a minus 120. We are dividing this entire expression by the binomial a minus 5. We will perform algebraic long division to find the remaining quadratic. We look at the first term of our dividend, which is a cubed. We divide a cubed by the first term of the divisor, which is a. This division gives us a squared, which is the first term of the quotient. You write a squared at the top of our division workspace. Now we multiply this a squared by the entire divisor of minus 5. Multiplying a squared by a gives us the a cubed term back as expected. Multiplying a squared by negative 5 gives negative 5 a squared. We place these terms underneath our original polynomial to subtract. We must be careful with our signs when performing this subtraction. We subtract a cube from a cubed, which leaves us with 0. We subtract negative 5 a squared from 0 a squared in our dividend. This subtraction gives us a positive 5 a squared moving forward. We bring down the next term from the original polynomial, negative a. Our new working expression is exactly 5 a squared minus. We divide the first term, 5 a squared, by the divisor term a. This division results in a positive 5a for our quotient. We write positive 5a at the top next to our a squared term. We multiply this 5a by the entire divisor a minus 5. 5 a times it gives us 5 a squared for the first part of the product. 5 a times negative 5 gives us negative 25a. We write these new terms below our working expression to subtract. We subtract 5 a squared from 5 a squared to get 0. We subtract negative 25a from the negative a term. This becomes negative a plus 25a, which gives 24a. We bring down the final term, the negative 120. Our final working expression is 24a minus 120. We divide the 24a by the a in our divisor to get 24. We write the positive 24 at the very top as the final term. We multiply the 24 by the divisor a minus 5 once more. 24 times a gives us exactly 24a as expected. 24 times negative 5 equals negative 120. We subtract these terms from our working expression and get exactly 0. The remainder is 0, which confirms our polynomial division is perfect. Our division gives us a quadratic factor to work with right now. The quadratic is a squared plus 5a plus 24. Our original equation is now factored into two separate pieces. We have a minus 5 multiplied by the new quadratic expression. This entire product is equal to 0, so we analyze each part separately. We already know the first factor gives the solution equals 5. Now we must check the second factor for any additional roots. We set a squared plus 5a plus 24 equal to 0. We can use the discriminant to check for valid solutions here. The formula for the discriminant is b squared minus for a c. In our specific quadratic expression, the value of b is exactly 5. The value of a is 1, and the value of c is 24. We calculate b squared, which is 5 squared, equaling 25. Next we calculate 4 times a times c for the second part. 4 times 1 is 4, and 4 times 24 is 96. We subtract 96 from our 25 to find the final result. 25 minus 96 is equal to exactly negative 71. Since this is negative, this part has no real solutions for us. We do not need to worry about this quadratic piece anymore. We can now confidently state the final result of our problem. The only real solution to this entire equation is a equals 5. We will now verify this solution by checking it in the original equation. Our original equation was a times a minus 1 times a plus 1. We substitute the number 5 everywhere we see the variable a. The first part of the expression is simply the number 5 itself. The second part is 5 minus 1, which calculates to exactly 4. The third part is 5 plus 1, which evaluates to exactly 6. We multiply these three resulting numbers together to check the total. We multiply 5 by 4 first, which gives us 20 as a result. We then multiply this 20 by the final number, which is 6. 20 times 6 gives us a total of 120. This matches the right side of our original equation perfectly. Both sides equal 120, confirming our work is correct. The value of is indeed 5, and our verification is complete. This brings us to the end of our math problem for today. Thank you for spending some of your time watching this video. Please leave a like on the video and subscribe to the channel. I will see you in the next mathematics video very soon.